Chapter 7. The partition equation emerges. There is a most profound and beautiful question associated with the observed coupling constant E, the amplitude for a real electron to admit or absorb a real photon. It is a simple number that has been experimentally determined to be close to 0.08542455. My physicist friends won't recognize this number because they like to remember it as the inverse of its square, about 137.03597, with about an uncertainty of about 2 in the last decimal place. It has been a mystery ever since it was discovered more than 50 years ago, and all good theoretical physicists put this number up on their wall and worry about it. Immediately would like to know where this number for a coupling comes from. Is it related to pi, or perhaps to the base of natural logarithms? Nobody knows. It's one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding by man. You might say the hand of God wrote that number, and we don't know how he pushed his pencil. We know what kind of a dance to do experimentally to measure this number very accurately, but we don't know what kind of a dance to do on the computer to make this number come out without putting it in secretly. Richard Feynman. For years, I chased a single thread. What does the fine structure constant mean? Not just because it governs the strength of electromagnetism, or because Dirac and Feynman thought it was the simplest keyhole into the rules of reality, being dimensionless, but because it shows up more than 100 times in the constants of nature, binding Planck constants together. Behind that prolific number was a riddle to unlock, a riddle directly related to the Planck constants. I read every paper I could find about the fine structure constant, every attempt to derive it from geometric principles, every speculative connection between known constants and dimensionless ratios. Many had tried. Some had found numerical approximations, the best of which landed 5 digits, rarely more. Euler's constant was among the champions of simple combinations that reproduced the fine structure constant to high accuracy, 5 digits, but it offered no pathway to understanding, no invitation to meaning. Then, on March 21st, 2019, an email arrived from Philip Preetz. He knew I was searching and pointed me to a blog post by Hans de Vries. In it, de Vries observes something remarkable. An expression involving only E and pi that approximates the square root of the fine structure constant. That claim caught my attention, but when I checked the math, the match was stunning. 8 digits correct, making his approximation 1,000 times more precise than Euler's constant. Even more shockingly, it did it with a formula built only from E and pi. This wasn't just a better fit. It was an equation representing a purely geometric form, a structural shape that could be looked further into. De Vries's approximation wasn't just better than Euler's. It provided a structural signature, revealing a form with symmetries and roots. This was a pattern that whispered of geometric meaning. But should I investigate? Or treat it as a coincidence? After all, the number we are talking about generating with this geometric rule is not the correct number. It may be the closest anyone has ever come to the correct number using simple algebraic expressions, but it does not faithfully represent the measured number. Specifically, its value is 18 sigma off, falling outside the error bars of the measured number by about 18 times the size of those error bars. Up to 5 is acceptable in science. The simple geometric structure of de Vries's equation made it impossible to ignore. I needed an equation with exactly that kind of geometric power, but I needed it to accurately characterize the fine structure constant, so I could use it to get to know that number. So I asked, what would it take to correct de Vries's equation? How far off is it really? To find out, I subtracted a small correction term, x, and then plugged in the measured value of the fine structure constant to solve for x. Immediately, I recognized the power of the number, -8, the same exponent as in the Planck mass. So I looked up the digits of the Planck mass, and there it was. The correction term, what the equation missed, was equal to the magnitude of the Planck mass. This was a structural clue. Hyperbolic spaces are distinguished by the scale of their mass gap, the space between the two-sheeted hyperboloid of their structure. A hyperbolic structure with a Planck mass gap would be the perfect constructor of Planck boundaries. I rewrote de Vries's expression, centering it on the square root of the fine structure constant instead of the fine structure constant, and setting the scale of its mass gap equal to the Planck mass. This produced the hyperbolic partition equation. The structure of this equation, its interplay of reciprocal terms, was telling a story of inversion, balance, and emergence. This equation characterizes a hyperbolic geometry that is perfectly structured to partition within the Planck mass gap. It builds a bridge between the geometry of exponential growth, circular symmetry, and quantum coupling, governed by a hyperbolic balance. If the binomial constructor enforces the cohesive union of two layers of Planck boundaries, the partition equation encodes the partition logic of those boundaries, defining how the system subdivides into persistent subsystems. Looking closer, we discover the rich algebraic geometric structure of this equation. For example, the hyperbolic partition equation has 4 solutions, not just one. The square of this equation's first solution gives a number that matches the measured value of the fine structure constant with an accuracy of 1.14 sigma. But that's just the beginning. This number comes with a complete algebraic structure that defines some of the most beautiful relations in all of algebraic geometry. For example, the product, sum, and quadrants of these hyperbolic partition constants define the algebraic structure of a projected sphere balanced over a single inversion. Their product is 2 pi, their sum is 0, and their quadrants, the sum of their squares, is negative 4 pi. The first of those quadrants is the fine structure constant, now revealed as a part of a highly ordered algebraic geometric structure. In that structure, it comes with 3 quadrant siblings, J2 squared, J3 squared, and J4 squared. Behind the fine structure constant stands a full architecture. The built-in symmetries of that architecture reveal the identities it keeps. These hyperbolic partition constants possess dozens of simple algebraic geometric symmetries, defining a richly connected geometric system bound as a 4-symmetric quadratic structure. Once we are aware of this partition structure, we can investigate the construction of each constant of nature in terms of it. That is, we can check every constant of nature against the possible subsets of simple transforms within this structure, the partition groups that define single-dimensional outputs. These are the 2-part products, the 3-part products, the 2-part sums, the 3-part sums, the 2-part quadrances, and the 3-part quadrances. Adding 2 polar representations for radius and angle to those 6 Cartesian subsets brings us to a total of 8 partition groups for characterizing the simple transforms of this coherent system. These define the full family of natural partitions related to the fine structure constant, the entire set of partition actions that coherently transform the structure it comes with. All other plural partial sets of these hyperbolic partition constants yield complex outputs and therefore do not represent simple transforms of the system. The ability to precisely reveal the algebraic geometric connections of the hyperbolic partition equation, all the structural cousins of the fine structure constant, leaves us perfectly poised to build a world from Planck constants, governed both by the binomial constructor and the hyperbolic partition equation, if only we had exact geometric boundaries to apply these rules to. With exact definitions for the Planck constants, we could precisely decompose every constant of nature in terms of geometric actions on those Planck boundaries. Doing this would enable us to check if the rules we are using reveal any pattern in the constants of nature. Chapter 8. The Hunt for Geometric Planck Boundaries. Before we can construct a world from 5 Planck boundaries governed by 2 structural rules, the binomial constructor and the hyperbolic partition equation, we must have precise definitions for those boundaries. We've already seen that the constants of nature intimately encode the 5 Planck constants, the 5 limits in the architecture of persistence: Planck time, length, charge, temperature, and mass. These boundaries form the structural edges of coherent atomic logic, and they show up everywhere, tucked inside the ratios and transformations that make physics work. But despite their foundational role, these constants are not known with full precision. This is not because our instruments are imprecise. It's because the Planck constants are derived from various combinations of constants of nature. The constants of nature are structured by the Planck constants in two parts. Different combinations yield slightly different values, and though these combinations all converge for the first 7 digits, they diverge beyond that. This divergence is a signal. It reveals something hidden in plain sight, a two-part structure. If we want to build a unified system from Planck boundaries, we can't use fuzzy quantities. We need the boundaries to be exact. We need them to be defined, not just partially extracted, and that means that they must be given geometric definitions. That became the mission, to hunt for geometric expressions that could stand in as true definitions of the Planck constants. Not approximations, not extractions, real geometric actions, simple, structural, and exact, that return each Planck constant's value. If the Planck boundaries are real, if they're the structural anchors of nature, then there must be a geometric logic that pins them in place. So I began searching. I sought every geometric expression for the Planck constants that was simple, modular, or structurally meaningful. Anything composed of natural geometric elements like e or pi, and functions such as sine, cosine, hyperbolic sine, or hyperbolic cosine, that produced the measured values of the Planck constants with full precision. The search took years. I used Wolfram Alpha to look for every algebraic geometric instruction that returned the experimentally observed values with full precision, and then systematically explored building the constants of nature from every simple geometric expression I found. Of course, precision alone wasn't enough. I was searching for 5 expressions that could work together, 5 geometric boundaries that shared the same internal logic, respected the same symmetry framework, and hinted at a common geometric ancestry. So my search was narrowed by 2 key constraints: simplicity, expressions with cleaner algebraic structure were favored, and hyperbolic character, expressions whose elements appeared naturally in hyperbolic geometry. The geometric expressions I found were then used to build the constants of nature, allowing me to search for a pattern in them. Each Planck constant comes with a completely known whole number exponent, its quantized power, and a partially known string of digits that defined its magnitude. That is, the quantized aspect of this boundary is completely clear, but its magnitude is less clear. Eventually, it occurred to me that the simplest possible characterization of each Planck constant would be one that matched both of its features to one geometric action. And the simplest way to do this is to interpret each Planck constant as a quantized plane wave. To treat each Planck constant as a quantized plane wave, we assume it is a combination of some geometric action A scaled by e to the b that produces its own quantized power psi. This allows us to search for a geometric expression A that matches the 2 aspects of the Planck constant together. To unveil each Planck constant's hyperbolic structure, A, we set B equal to its partially known magnitude and psi equal to its quantized power. This constrains the possible values of A, the hyperbolic boundary that maintains this action. And then we search. We ask Wolfram Alpha to show us any algebraic geometric prescription that characterizes that exact number. This time, I found something. Wolfram Alpha revealed 5 simple hyperbolic actions that produce the right scale for each Planck constant. 5 candidate expressions, simple, modular, hyperbolic, each built from the language of geometry, each structured as a quantized plane wave that returns the full known value of each Planck constant. Together, these expressions have a shared coherence. They respect the same symmetry logic. They use the same kinds of ingredients: cosine, hyperbolic sine, pi, e, I, and the Weierstrass constant. Their architecture felt consistent, mutually informed, and this was what I had been looking for. Of course, this does not mean that they are the true definitions of the Planck constants. Not yet. At this stage, they are still hypotheses, tools in the toolkit. But they are exact tools from which we can now attempt to compose the constants of nature. To earn their place in the theory, these candidate Planck constants must pattern together the constants of nature under one rubric, a rubric that should then, in turn, justify those inbuilt bounds. Discovering that rubric is our aim. So I began using these quantized plane wave definitions of the Planck constants to deconstruct every constant of nature through the logic of the binomial constructor and the hyperbolic partition equation. I had tried many possible sets of definitions for the Planck constants at this point, finding very little clues to follow. But now, with these quantized plane wave definitions, I was able to find a pattern that, over the next couple of years, grew to envelop every constant of nature, all 288. With each new constant decoded, the pattern became clearer and more striking. A single structure was emerging, woven throughout the constants of nature, and the geometric components of this structure, the actions responsible for maintaining each boundary, could all be traced to a common source. Not only did a pattern emerge, all of the geometric components in that pattern turn out to be logical derivatives of one geometry, boldly giving away the geometry that structures reality together. In the next chapter, we will begin examining this pattern, starting with how it decodes the three constants of nature that fit the Dirac equation together. We will find that the geometric components of those constants map precisely onto the structural powers granted into the world by one specific hyperbolic manifold, revealing the geometry that sustains the unitary logic of the Dirac equation.